Thank you, madam. Right, we'll see if it works. So just in case they can't see, I don't know whether Kibera can see, but if they can't, Mathare, you've got good band Wi-Fi and everything. I'm really impressed. And you're still looking clever. You're still awake. How are you still awake? This is chemistry. Oh, no, it's good. No, chemistry is good. I forgot. Yes. Okay, so here we go. So I'm now going to give you one to do, and it's going to be really hard. Are you ready for that? Yes. No. Yeah. Good. I like you. Okay. So, and I'll show you. This is why this is powerful, because this allows us to work out absolutely any one of those moles questions which we often get. So my question is going to be an excess of CaCO3 was added to 100 cubic centimeters of 0.5 m HCl. What volume of CO2 is produced? Okay, there's the question. Here's the equation. So it's an excess of calcium carbonate. So we're adding HCl. So it's HCl, it's going to be 2HCl plus CaCO3 goes for CaCl2. It's a carbonate, so it's going to form a salt and water and carbon dioxide. And so it's the hydrochloric acid going to the carbon dioxide. So the small box is going to start here, and then we're going to get a big box here, and we're going to have the ratio on here, and then we're going to have a small box here, and then a big box. In this one here, we're going to use the solutions triangle. In this one here, we're going to use the gases triangle. Okay? Because in here, we've got 100 cubic centimeters of 0.5 mole per cubic decimeter. Now, I can use the triangle to turn this into moles here, because I'm not going to do this now. I'm going to ask you to have a go. Because from that triangle, moles is concentration times volume. Over here, we're going to use the gas one, where the volume equals something. So have a moment, have a go, because I'm just going to go over there and get ready for a little practical to show you. Okay? Finished? quite. Hello, Michael. Ooh, God, that's quick. Patrick got 600 cubic centimeters. Patrick, you're a genius. Patrick, you are a genius. Let me see Patrick's face. Patrick, you are a genius, sir. Well done. You are first. You get gold medal. He is the Eliud Kipchoge of the calculation world. Oh, brilliant. Who's that? Michael, you've got another one. Kibera, 600. This is so easy. Okay. Now, oh, very good in cubic decimeters. Well done. Well done, guys. Okay, so simple. If you see that it is simple, if you can use this is a method all the time, it is really simple. And I promise you, they will be able to use this at university. If they get to university and they use and they do chemistry or some other mole-orientated subject, they will be able to do it there. Okay, so I'm going to do a little experiment. I'm going to show you a small experiment. And a small experiment goes like this. We'll do another calculation like this in just a moment, but I'll get rid of it. So, sorry, I should go through it just in case people are not sure. So I get so my moles is concentration times volume. That's 0.5 times. Remember that your 100 cubic centimeters has to be turned into cubic decimeters, liters, mils into liters. So that's 0.1 equals 0.05 moles. Now, your problem is remembering that you've got to have the ratio on the arrow. And because the ratio we have to, and a lot of students find it difficult to find ratios. For some reason, they don't realize that when there's nothing in front of it, it's 1. So the ratio is the hydrochloric acid to the carbon dioxide. So it's 2 to 1. And if the 2 to 1 starts with 0.05, then it's going to be 0.025 over here. My gases calculation, sorry, my gases triangle calculation, the gases one says that moles is down the bottom, the volume which we measure, the thing we measure is at the top, and 24,000 or 24 is down the bottom. If we're assuming it's room temperature, in the question they will always tell them whether they want to use 24 or 22.4. So volume is moles times 24,000, not enough room, equals 0.025 times 24,000, which is 600 cubic centimeters, or 0.6 cubic decimeters, which is really good. Was that okay? Is that a method which you think you might use, do you think? Because I promise, in my experience, I have used this. I've worked in 7 schools, 1 in India and 6 in the UK. One where I was unfortunate enough to meet Mr. Yestin Thomas, and he asked me to do this. 6 schools, and every single one of them, after the first one, where I had problems teaching moles, I came up with this method, and after that, it was like easy, honestly easy, and my students all can do moles straight away from age 14. Age 14, they can do this. So that's a big math. Okay, so I'm going to do an experiment. I'm going to go to the other camera. I'm going to show you one which I think, oh, no, first, here it is first. Glass of water. You may have come across this stuff. I hope you don't have to take it. It's not very good for you. Alka-Seltzer. It's for when you have had too much Bugatti and alcohol. So you're not allowed to do that. So this Alka-Seltzer is an effervescent mixture. In this country, because we don't have enough citrus fruits, we are often encouraged to take these. These are vitamin C tablets. Okay, we don't have oranges, sadly, not enough. So we're encouraged to take these, and these, when they go into water, they just effervesce, just like an Alka-Seltzer. But the advantage of these is that they're coloured, and they fizz quite a lot. And I was trying to think of a simple way of working out the amount of chemicals in products which the students come across regularly. I don't think I'm going to drink that. It smells horrible. But I'm going to show you an experiment using it. So my idea was, hang on. I know that in these tablets, there is sodium hydrogen carbonate and citric acid. If there's citric acid is a tri-basic or tri-protic acid. And so when they add water, the hydrogen ions are liberated. So H3A, I'm not worried about what the A is on citric acid, dissociates like this. It's a weak acid, and therefore this is well over to this direction, but bit by bit, it dissociates more as that is used up. So in the effervescent tablet, there is NaHCO3 and the citric acid. So this is going to react to make Na3A and water and carbon dioxide. I'm going to need 3 of these, so I'm going to get that. Whoops, sorry. I'll let you work out how many waters and carbon dioxides while I just go over the other side of the camera. Okay, just so you can make sure. My idea was this, and I'm going to show you how to do it. Really simple. If I could find out how much carbon dioxide was produced, I could work out how much sodium hydrogen carbonate was in each tablet. Okay, so I thought, okay, let's see if we can do that. So I'm going to show you a rather poor experiment, but one that can be done with just one tablet, some water, and either a measuring cylinder or something like a glass on which you have marked volumes which you have measured once. Okay, so I'm going to go over to the other camera. Okay, I shall be there in a moment. So, hang on, I need to turn around my monitor so I can see what I'm doing. Okay, I'm here. So I have here a trough of water, really simple. I have a measuring cylinder. It wouldn't have to, like I said, it wouldn't have to be a measuring cylinder. You would have to work out about how big a measuring cylinder you need first. I'm going to put my hand over the top because I need to collect the gas. So I'm going to turn this upside down into the water. And now I have it hopefully mostly full of water. I could do this in many ways. I could have a delivery tube, I could have a beehive shelf and so on. But I thought, wait a minute, what happens if I want to do it really simply? So I do it really simply. So what I'm going to do is I'm going to take this tablet and I'm going to just put it in there. Now, a little bit of the carbon dioxide will disappear. I will miss, whoops, hello, don't knock it over. I will miss a little bit of the carbon dioxide because as it goes in, but this is a good way of describing errors for your students. I'm going to stand it on something so it doesn't just drop out the bottom when I put it underneath. So here we go. Let's see if I can get it to work. Okay, now the advantage of the color is that the color can show you quite easily where the gas is. You can see the solution going down. That's quite clever. And it is reacting, it's producing quite a lot of gas. It's going down fairly slowly, but you can see the gap at the top. We're going to take the results of this. Let's see if we can get a little bit closer with the camera. There we are. So you can see it going down, nice and orange. Now, if you didn't have these orange, you could color the water with some ink or some vegetable dye or something like that. It's nearly finished, and you won't probably be able to read this. We'll just see. Let's just see if we can get you close enough to be able to read this. Oh, it can't focus. Come on, focus. Oh, such a stupid machine. I don't think you'll be able to read it, but this is saying 136 cubic centimeters. Okay, 136 cubic centimeters. Okay, come back to this side of the world. So, looking at the equation, what's wrong with the equation so far? Can somebody just balance it up for me? Doesn't look right so far. Anybody? Show me fingers if you want. How many waters? Or how many carbon dioxides? The carbon dioxides are easier. How many carbon dioxides? Have courage, teachers. You have to, one of the things I have found as a teacher is I have to teach them to be willing to be wrong. This sounds like a really strange thing to do, but and I'm sure many of you do it all the time, and I'm sure you're really great at this. I'm not very good at it because I am tempted to go, oh no, you got that wrong. And I go, okay, now I have to learn to say, okay, why do you think that? Not, that's stupid. I have to let them have a go at getting it wrong. So somebody, come next side, how many? There it is. Oh, have courage, teachers. Have courage. Look over here. It must be 3. There's something wrong with the waters as well, but we're not going to worry about that for the moment. 136 cubic centimeters. So I'm starting here. And what I want to do is to work out how much of this I get. So the small box is here. Then there is a big box here. Then there is a small box here. And then a big box here. And here, I want to know how many grams of sodium hydrogen carbonate I have. Okay, how many grams of sodium hydrogen carbonate? So, see if you can do it. Just see if we can work out from this what it says we've got in here. Okay, let's see if we can work out the mass of sodium hydrogen carbonate in 1 tablet of effervescent vitamin C. Is that waters? Very good. Now, we want to try and work out from the 136 cubic centimeters of carbon dioxide what mass of sodium hydrogen carbonate we have. Sophia, is lunch in 20 minutes?
Yes, teacher Mark, we break at 1.
At 1. Cool.
We have an answer.
Good. Hang on, I'm just coming. Sorry. I was just getting ready for another small piece of juju. Let me just turn this around. Okay, let's see an answer. This looks...
476 grams.
Say again. Sorry, I did not.
0.476 grams.
.476 grams is exactly right. Thank you very much, teacher. Very good. Now, I know this is not fantastically complicated for you, but the point is, we have here a really simple experiment which could be done for the cost of a few Alka-Seltzers or one Alka-Seltzer that you could show. We can do the calculation. They can find that they can do an analysis. A really quite complicated analysis, because this has involved them understanding 2 of the triangles, the 4 boxes, how they're related by moles, ratios, the whole thing. Just before lunch, because I know you only have 20 minutes before. Your stomachs must be rumbling. Your tummies must be going, ooh. So just check that you've got that there. Let's just go through it. So I have here, I work out moles. Moles is the volume of gas which I have divided by the volume of 1 mole. So it's 136 over 24,000. 136 divided by 24,000. Now, I don't know whether it's the same for your examination board. For our examination board, they don't mind if you write this as a fraction or a decimal, doesn't make any difference to them. But I'm going to put it in as a simple, I'm going to simplify it to 0.0056. I know it's recurring. The ratio is 3 to 3, so it's 1 to 1. So I don't need to worry, that just transfers 0.0056. Mass is equal to, from the triangle, the masses triangle, is equal to moles times RMM. Sodium hydrogen carbonate will weigh 23 and 1 and 12 and 3, 6, whoops, not that, and 3/16, which is 84 in my head. So my moles is 0.0056 occurring times 84, and that comes out as 0.476 grams. Nice. Okay. So, simple practical, simple way to do something. You could make it as complicated as you wanted. You could have gas syringe, you could have conical flask, everything, but it really works. So on to the most complicated bit. It's only complicated because it is about redox titrations, okay? So redox titrations go like this. So I'm going to pose a question to you. I'm going to set up a question. I'm going to show you how it works. I'm going to then ask you to do it, okay? When we use potassium manganate 7 or potassium manganate, permanganate, MnO4 minus, a lot of Form 3, Form 4 students find it very difficult to balance equations with this. We use oxidation numbers, which are like valency, as you know, but let us assume that they can put together two half equations. So when this reacts, because this is in a +7 state, and it turns into Mn2 plus, which is a +2 state, obviously, it needs 5 electrons. It also needs to get rid of 4 oxygens, so it needs 8 protons to make 4 waters. That balances, that's okay. If I then have the oxidation, so I'm going to use it in a titration, and I'm going to oxidize iron 2 to iron 3, then I balance my equation on the electrons, obviously. 5 electrons here, 1 electron here, 5 times all of this equation, so I get that's what my equation is going to look like at the end. This is why I have to add acid when I'm doing a redox titration. One of the things which I did last year before, when we were trying to train Form 4 pupils to take paper 3, I did some how to do a titration and so on, because some of them obviously hadn't before. But I'm sure most of you train your students very well. It's just sometimes it's difficult without the right equipment. So let us say that we have started with a certain mass of iron. And this mass of iron has been put into a 250 cubic centimeter flask. Okay, so the iron as a metal has been put into here. I then take out, using a pipette, 25 cubic centimeters of the solution. I titrate this against 0.02 m KMnO4. Okay? All right? I'm going to say that the volume which was used is 18.05 cubic centimeters. What I want to know is how much iron I put in here. Now, what I'm doing here is I'm modeling something which I model for my students. In the question, it would say all that in words. It would say an unknown mass of iron was dissolved in sulfuric acid, made up to 250 cubic centimeters. 25.0 cubic centimeters was pipetted out into a conical flask, which was titrated against 0.02 potassium manganate, and it would give a table with the titers. Why I think this works is that it helps them to follow the track through the calculation. In other words, they're going to start here. They're going to go to here. They're going to go to here. And they're going to go to there. In other words, I'm going to work out the moles here. That will allow me, using the ratio here. This is like the big box. This is the small box into a big box. This is the ratio. This is how many moles of iron there is in here. This is 10 times that, and that will allow me to work out the mass of iron. So, just to show how clever you are, let's see if we can do this. Let's see if we can do this calculation, but try and see what I'm doing here. I'm trying to make something which comes out in a lot of words into something which they might be able to sort of imagine that they're doing. In other words, I'm trying to say, this is one of the triangles. This is going to be working out the moles of MnO4 minus, which will give me the moles of Fe2 plus. And that was 1/10 of the original. And that would allow me to work out the mass of iron. Just see if you can. I know it's hard. I know it's nearly lunch. But if you can see how you can turn words into pictures, sometimes it can help students understand what they're trying to do. Because a lot of students, they see a lot of words, no idea at all. And this is the hardest moles calculation they would ever have to do. And for most, actually many university courses, it's not going to get much more difficult than this either. Sure, we're talking about bigger RMMs and so on, more complicated looking chemicals, but this uses the solution triangle, the mass triangle, a ratio, a multiplication up. So if you want to just sit and go, oh, my brain has gone, that's okay. But if you want to see if you can work it out, we'll give out gold and silver and bronze awards, maybe. And maybe you get a second helping of lunch. Mrs. Kamwari? Yeah? Second helpings of lunch? More lunch? Michael's going to, I'm going to work it out.
I'm up for lunch.
I'm up for lunch. I'm very
up for lunch. I'm always up for lunch, mind.
Well, yeah, I'm always up for lunch. I should have said that the the RAM of iron we will take as 56. You don't need the RAM of that because it's a solution triangle.
Raised platform. And that's
I'm teaching you business
We have an answer.
Oh, yes. That's fantastic. Wow, these guys are very good. I'm really glad. Well done. Thank you. That's a really great answer. Thank you, Patrick. Patrick again. Patrick, you don't need my help. But if you find some of the ideas, the ways of simplifying things and giving them patterns helps, then that's great. Teacher Patrick has already got the answer. If other people want to get the answer, that's fine. We're going to break in just a moment. I'm just going to show you something before we break, but have we got any more answers? The answer is just over 1 gram. The answer is just over 1 gram. And it goes like this. If I take this 18.05, what I'm going to do is I'll do it as the 4 boxes and then you'll see where it is. But basically, this is going to be from the solution triangle, moles equals concentration times volume. So 0.08 times 18.05 over 1,000. That's the moles of KMNO4. Then we do the ratio. The ratio is 1 to 5. So we multiply that by 5 to produce the moles of iron in here. This was taken out of 250. So this is times 10. So here, times 5, here, times 10. That will give me the moles here. And here, the amount of iron, grams, is moles times RAM. The RAM is 56. And the answer comes out as 1.011, approximately, 1.0108. Okay, now it's basically time for lunch. This is the timing for lunch. Let me just see if I can just change something. Okay, here's the timing for lunch. Let's have a look. This should work. 25. Okay, 25, 40, 80. So when something happens here, you may go for lunch, ladies and gentlemen. I hope this morning has been useful. If it hasn't, okay. If it has, oh, it must be lunchtime. Maybe it's not. Oh dear, time has gone again. Okay, that's really simple. Okay, I hope that was useful. After lunch, we're going to have Mr. Yestin Thomas waking you up and giving you some ideas about how to motivate people and so on, which is excellent. I've seen his talks before and they're very, very good. Some of you may have seen them before, in which case you know how to wake up again. After that, we will be doing structure and bonding. It's easier than the stuff we did this morning. What I want you to remember is the structure of the lesson. Start with something interesting. Tell them where you're going. Give them lots of practice so that they do lots of the work. And then tell them where they went. By the end of this, you have now got 3 triangles, 4 boxes, and a method for doing the empirical formula. And if you can, that in like 2 hours, that's a lot of moles on method on how to do moles. I know that you personally can do this, but what I'm trying to do inexpertly, and I'm sure many of you have got a better idea, but I'm trying to get you to think back to when you couldn't do this stuff too. To Teacher Patrick, who is the winner for this morning, congratulations, you get the second helping of whatever you're getting for lunch. But for everybody else, I hope we will be seeing you in, is it about an hour?
How long have you got, Sophia?
Headmistress, wake up.
About an hour.
We've
Cool.
got an hour. So
Okay.
Okay, so
I
we're
hope
back
you
at 2. Okay.
I
All
hope
right,
you.
so
I hope you have a brilliant lunch. Thanks, Michael.
2 o'clock on the dot. There we are.
Asante. Yeah.
That's a quick one. It's okay. That's a quick one. Slide. Look,
Kibera, time to go for lunch.
I'll give you a quick call now, Mark.
Okay. Oh, hang on. Somebody's saying something. How do you achieve introducing Mars to a student at age 13? Okay, Michael. Michael, I've got a question there. How do you introduce moles without having done chemical symbols and chemical reactions? I introduce chemical symbols and chemical equations at age 11. We do not worry about balancing equations. We do not worry about too much detail on it, but we effectively what we do is we introduce it all, I think, quite a bit earlier than you do. I'm not suggesting that you bring it in at age 13. I'm not. I'm suggesting that you do it at an age which is appropriate and you bring this in as soon as you can, and hopefully that will make sense. Okay? I'm just going to look in the chat.
Okay.
Thanks, Mr. Oh, okay, Sean, thank you very much. Nice lunch. Good. I'm glad it's a nice lunch. I'm really glad. Okay. Hi, Yasin. I'm just going to.